Hello, I am Sohail and this is part 1 of my DFT instruction. I try to explain everything as fast as possible. Ne- Necessary thing, not everything. So, first of all, we need the structure of our crystal. And for that, I use this site, Crystallography Open Database, but you can use any other site like Materials Project or other sites. The important thing is we need this zip file for our crystal. For this instruction, I work with sodium chloride crystal. So let me get the crystal structure file first. Here I use this file. Each zip file is from one paper, and here is its reference. So I use this file, I download it, it's download. Okay. After that, we need to convert this zip file to the file that Quantum Espresso software can read it. Quantum Espresso can read zip file directly, so we need to convert it. So here is our zip file. I open terminal. You can also download the zip file by wget command. For example, if I copy the link here and paste it, I can download it in terminal too. So here for converting our zip file, I use zip to cell. First I need to open my environment. Panda activate QSpresso. Yes. Okay, now I use zip to cell and the name of our crystal file 1000. Okay, -p, and here you write the program that you want to convert to it. Quantum espresso, and here I write the name of the output file. For example, basic.in. Okay. Wait. Okay, now our file converted. It's here. Now we open the file. Here I open it with Nano, but you can use any other text editor. Nano basic. Okay. Here it has some information for us, and we should change or add some blocks too. First we need to add a block like the system block, but here is control block. We write first calculation equal to SCF. SCF is stand for self-consistent field method or Hartree-Fock method. It's not important, it's just for calculating total energy for us. Next, out directory. Prefix. Here I put in name of our calculation, for example, just basic. Next, sudo directory. For sudo directory, we first need sudo potentials file. So I need to download it. I go to, if I write it correct, http, let me just search it. Sudo potential quantum espresso. Here it is. Okay, now here we just click on standard solid state potentials. It's rotating. Okay, now here we come sudos. You can download each element separately, but here I download all of it. As I downloaded before, I cancelled it. Here, after you download, you should just unzip the file with let me make another. After you download the file, you should just unzip it, for example with gunzip ssv.tar.gz. After that, tar xvf ssv.tar, and after that you have a folder like mine. Let me find it. I think it's here. Yes, and here you have all elements pseudo potentials. For example, here is for aluminium, barium, carbon, and all the elements, periodic elements. Okay, so I should put the folder name here. Let me just copy that. I just put it here in sudo directory. Okay. After that, we need verbosity. Sorry, verbosity. This parameter is not necessary. Not necessary to know. They always are. This parameter doesn't need to change. Yes. Okay. True. Don't forget it has 2 dots. Okay. After that, PS stress. And we close this block. Okay. Next we go to system block. IBRAV. This is the length of our crystal cell, and this shows how many atoms do we have in our crystal cell, and this parameter shows how many different type of elements we have in our crystal cell, unit cell. They are defined by our zip file, and we don't need to change it. Here our different type of elements is sodium and chloride. Next I add cat. Oh, sorry. Oh my god, don't panic. Let me check. Yes. Okay, as it deletes all my command, I decided to write it in text editor instead of terminal. So we are here. I add bcat and ecat rho. These 2 parameters have to change, and we should find the optimal values for these parameters. I talk about them as soon. Okay. For now, let them go. I add input, DFT, PB, occupations. It's just for approximation. It's not important. Smearing, and smearing need to be MV, and Eos is equal to 0.530. Okay. and we close the block. After the system block, we need electron block. Here we have convention threshold equal to, I think it's good, and mixing beta 0. Now here we can see our cell parameters, our atomic species, sodium and chloride, and our atomic positions too. We need to put the name of the pseudo potentials here for sodium and chloride. So I go to our pseudo library, I find it, okay, and here I need to find sodium and chloride. Here is sodium. I just copy and paste it here, and for chloride here. Make sure that input DFT PB, and here we have pseudo potentials for PB. They should be the same. Okay, next we need K point. Just under the atomic positions, I add K points. Automatic, and here, for example, I put 3 3 3 3 3 0 0 0. For converging test, we need to find 3 values, 3 parameters. First, ECOT, WFC, second, ECOT, RHO, and third, K points. Just these 3 values. The second 3 values are for offsets that we don't need. What is WFC? ECOT is like a Fourier series. In Fourier series, when we want to make our function with basis function, sine and cosine, we sum the cosine and sine on infinite numbers, but the computer can sum in infinite, so we should sum in the finite number of basis function. So ECOT describe the number that we put here. In DFT, we want to describe the electrons' orbitals with plane waves. Our basis function is not cosine and sine; they are plane functions, plane waves, and we should sum the plane waves over finite number of. We should describe electron orbitals with finite plane waves. So we need to find this option parameter, and after that we also need this parameter. It's like this, but for another part. One time we need that for reciprocal space, and one time we need that for density space. It's not important, we just need to find these 2 numbers. This second number is the ratio of this number. We should find the number that when we multiply to this, we come to this. I explain it more soon. And after that, we need to find these K points. They are, for example, if I want to make it clear, in reciprocal space, the space that we calculate the properties of our materials, it's infinite space, it's continuous space, but we need to sampling a finite points. For example, when I write here 333, I mean that for my sample I put 3 points in this axis, 3 points in this axis, and 3 points in 0 axis. We should find the more sample point, the more precise calculation, but also the more k points, the more computer price and more time. So we need to find optimal values for these 3 parameters. Okay, for converging test, first we work on k points, and for that we change k points and find the hydrostatic pressure and typical runtime, and after that we find the optimal k points values. Why we use hydrostatic pressure? Because this property is an experimentally observable property that is rather sensitive to numerical precision. If this property is converged with respect to our k points, many other less sensitive properties will be converged too. So it's ideal to work with hydrostatic pressure. I run one time this program, and after that I just show the result. For now I first start my test with just one k points in x-axis, y k points in y-axis, and 1 k point in z-axis. I save this file. I think it's good. Okay. How we should run this program? It's easy. Just go to download. Yes, it's here. Our basic file. With this command, first we got input basic in. Next we should name our output basic.out, and that's it. Oh, first we need to activate our environment. Activate conda, activate q. Okay, now we run our command. And now we should wait. Okay. Don't worry about this error warning message. It's not important. So, as our k points is very low, just 1 point in each axis, the calculation run so fast. So here, if I come to download basic.output, here is our output. Oh, let me see what's happened here. Oh, I think I write this line wrong in here. Let me check. Oh, I forgot to put a comma here. Okay, now it should work. Out. Wow, too fast. Let me check it. Oh, what's happening again? In programming, errors always happen, but we don't fear of them. Oh, here I put comma. It should work now. Oh, I just forget to put n here. Occupations. Yes, now it's work. So now we should wait until the program finished. I just paused the video. Okay, now it's finished. As I said, this warning is not important. So, yes, it's our result. for K point 111. Now we should find hydrostatic pressure. Let me just find it. Let me search. Hydro pressure. Oh yes, it's here. Yeah, I need this one. Here is our hydrostatic pressure. It's a tensor, and as it's hydrostatic, we have same values in x-axis, y-axis, and z-axis. You can think about it like this. If it is our crystal, we have same pressure here, here, and there. It also shows the runtime. I think it should be here. It should be here. Yes, here is your total energy, and here it's total runtime, 24 seconds. 24 seconds, and pressure, I lost it again. I think, yes, it's 261. You should write it in a table like this. Here we have K, pressure, and runtime. For example, here we have 1, 1, 1, 26, and I don't know, for example, 27, if I write 27 seconds. After that, you try some other K points, for example 3, and for example you got pressure 3. You can see that when we choose just 2 points more than our first decision, our pressure changed more than 200, more than 200. And for example, we can say that in my laptop the runtime should get 60 minutes. After that, you can also test 5, 5, 5, and for example it changed to 1, and also the runtime get to 70. Here we also have 2 negative change in pressure, but for example if we check 7, we got just 1.9, and the runtime should be here. As to me, I just work with this K point because its pressure is acceptable, because as I change the K point, it just change very low. You can test, for example, K point 999, and you see that the pressure should be just like this, but the runtime maybe it get to 240. So I just work with this K point 555 for this material because its predicted pressure is near to denser K point, and also it has a good runtime for me, so I work with it. After the K point, after we find our K point, for example 555, we go to ecut WFC and we just do the same work. First, keep the multiplication factor same. For example, here our multiplication factor is 4. 66 multiplied to 4 is equal to 264. So I again again I make a table. For example, ecut WFC ecut RTH and pressure and runtime. I keep the multiplication factor same. For example, here is 4. So here I have 66 and it's equal to 264, and for example after that I find my pressure be, I don't know, 100 kilobar and my runtime is 10. After that I change this to, I don't know, to 100 and I change ecut WFC to 100, and as I said the multiplication is 4, so here ecut RTHO is 400 and the pressure, I don't know, for example is get 10 and runtime is 6, and we change ecut WFC until that we find the value. For example it's 30, 20, 30, 23. I don't know what's the multiplication. It should be after that, and the pressure get 2 with runtime 2 minutes, and we see that when we change our basis size from here, the pressure doesn't change too much. For example, when we use larger basis size like 400, our pressure just change just a little, but the runtime is too much. So and after that another ecut, another. So I decide to work with this ecut, this basis size for our wave function, because its pressure is near to other pressure with larger basis size, and its runtime is good for me. If I need higher precision, I work with this, but for example the higher one, just change it, it's too little, so I work with that. After that we fix the ecut WFC, the basis size of our wave function, and we work on the multiplication factor that shows what's the value of ecut RHO, the basis size of density function. So here we work with factor 4, but we change we fix the wave function basis size. For example, here I choose 400, and again draw a table, pressure, runtime. Here my ecut WFC RHO, and I should write multiplication here. Let me just change this to factor. RHO, and my WFC is equal to 400. So first I start with factor 1, it gets 400, factor 2, 800. I just fix my ecut.ufc and my kpoints and just change ecut rho based on your multiplication factor. 3. You just need to check 1, 2, and 3. Your factor should start with 4. The first one is too low. So the rho here, get this, and after that 5, 6, 7, and just like previous values, we find ecut rho, the basis size for density function 2, and congratulations, you now can find the parameters for converge test. And after that you fix all of these and run the program quantum espresso file, and you get the output that here it shows your total energy in Rydberg. Thank you, and have a nice day.